Here are solutions to homework set number 9 for ECE 376 Embedded Systems. This homework set looks at interrupts. Now last week in homework set number 8, we looked at timer 2 interrupts, getting a single timer interrupt to work. This week we'll expand it to look at adding more interrupts, specifically the INT edge interrupts, as well as timer 0, 1, 2, and 3. Now the first problem looks at using timer 0 interrupt. With timer 0, I can measure time 200 nanoseconds. For example, right here, I am displaying time as measured by timer 0. I've got the low 16 bits, that's timer 0. The high 16 bits is just a counter. Every time timer 0 interrupts, I increment the counter. Put the two together, I've got a 32-bit time. I'm measuring time 200 nanoseconds. So if I stop it, I stopped it at 106.0143125 seconds after reset. Let it start over. I start from 0. And here's the time since reset, measured to an obscene number of decimal places. Okay, now that works, let's measure something. Let's start with how long I can hold a button down. So here I'm going to measure the time, wait until I hit button 0. When I press it, I'll record that time. Wait until I release it. When I release it, record that time, display the difference in time. So here's what that looks like. I press, 1 second later, release, actually held it down for 1.588306 seconds. 1001, closer, 1.0092919 seconds. With timer 0, you can measure time obscenely accurately. So let's go for quick. Fastest I can press and release. So press release. That was actually pretty good. That was probably bouncing. That was 58,466 clocks, or 5.8466 seconds. And I'm pretty sure that was bouncing. This is a mechanical switch. It bounces and records the time of the last bounce. That's more reasonable. That was 13 milliseconds, or 138,663 clocks. I'm getting a lot of bouncing here. Ooh, that was a long one. 1,025,511 clocks. Okay, that's how long it takes to press the button and release it. Another problem. Let's have a passcode. Passcode is 1234. How long does that take? So here what I'll do, I'll wait until I hit RB0 to start. I'll then wait until I press RB1, 2, 3, and 4. Record the time at the end. Display the difference in times. So let's try that. Now this starts the code 1, 2, 3, 4. That was 2.8774746 seconds. Let's do that again. Start 1, 2, 3, 4. 1.5098630 seconds. Let's go again. How long does it take to hit a button 10 times? So I'll wait till I hit RB0, record the start time. Wait until I hit the button 10 times, record the ending time, take the difference in time. That's how long it takes to hit the button 10 times. So here it is. I start 1, 2, 3, 4, 5, 6. There's bouncing going on. 1, 2, 3, 4, 5, 6. Well, 10 including bouncing. There's 10. So it takes me 2.1646389 seconds. So you can go faster. About 1.32 seconds is how long it takes me to hit the button 10 times. So that's timer 0. With timer 0, I can measure time 200 nanoseconds. That's really, really impressive. Next problem. With timer interrupts, I can play multiple notes at the same time. So I want to play 4 notes simultaneously. This kind of shows that interrupts do not interfere with other interrupts. I can have 4 of them running at the same time, not a problem. I'm going to have 4 different square waves being output at the same time. I want to output note D3 sharp, F3 sharp, G3 sharp, A3 sharp, or these frequencies. To do that, I calculate the number of clocks between interrupts. That's 10 million divided by 2 times hertz. That's equal to n. That's this number right here. I should have 32,000, 27,000, 24,000, 21,000. To do that, I'm going to use 4 different interrupts. Timer 0 is just prescaler times y. I'm going to have the prescaler 1, so this is y. Likewise for 2, for 1, likewise for 3. Timer 2 is a little bit weird. I need to have a times b times c is 24,000. Here's one combination. To do that, I need to set up T2con and PR2. PR2 is just b minus 1. So PR2 is actually 214. To get PR2, that's A and C. A is 7, C is 16. The bit pattern 1, 1 gives you 16. To get 7, this is binary 6, means 7. In hexadecimal, I split that. High 4 bits, low 4 bits. This is 3, and the last one is 7. So this sets up timer 2. And then the interrupt service routine, I'll just interrupt every n clocks. When timer 0 kicks in, I'll set up the next interrupt at 32,141 clocks in the future. It takes about 40 clocks to trigger the interrupt, so I'm just going to offset it by 40 to take that into account. Makes it a little bit more accurate. This number is probably a little bit off. Timer 1 is further down the code, so it takes a little bit longer to get to here. Timer 3 is slightly further down the code, takes a little bit longer to get to there. Timer 2, I don't have to mess with that. If I try that, I have 4 different frequencies. Measure the frequency on RC0. It is actually 155.7 hertz, up by 0.08%. On RC1, it is 185.2 hertz. RC2, timer 2 interrupt, 207.9 hertz. RC3, timer 3 interrupt, 233.4 hertz. So I can have multiple interrupts running at the same time. They do not conflict. Problem 4. Let's play Hungry Hungry Hippo. I want to have 4 different players playing. So here's what that should look like. I'm going to have your Pico board, or PIC board, displaying 4 different players, player A, B, C, D, and the time left. I'll start the game with RB0. That clears out the times and have 10 seconds. I can now hit the buttons. That's players B, C, D, A, and once the game is over, it stops counting. So in this game, player A won. So how do I do that? Well, there's a lot of ways of doing it. One approach is to use the 3 INT interrupts, that's button 0, 1, and 2, to count players A, B, and C. The 4th one, I'll use timer 0 to count for player D, and timer 2 keeps track of time, accurate to 1 millisecond. In that case, my flowchart actually has 5 subroutines, or 5 flowcharts. The main routine on reset, the timer 2 interrupt every 1 millisecond, and then INT 0, 1, 2, and timer 0. When I compile the code, that was 3362, or 5% of the PIC memory. The PIC can do a whole lot more than play Hungry Hungry Hippo. The interrupt service routines. On timer 0, if the game is on, I will increment D score by 1 and set up the next interrupt for 1 edge in the future. Timer 2, if time is positive, decrement to 0, stop at 0. Timer INT 0, increment players A if the game is on, likewise for 1, likewise for 2. I'll initialize. Timer 0 is set up for external event. That's reading port A pin 4. Timer 2 is set up for 1 millisecond. INT 0, 1, and 2 are set for rising edges. Then the main loop is I wait until the game starts. Once I hit button 0, that starts the game. I'll set the time for 10,000 interrupts. That's 10 seconds, or 10,000 milliseconds. Clear out the times. Set up player D. That will interrupt in the next 1 count. then keep displaying while the game's on. Display pair A, B, C, D, and the time left. And actually, that's not there. Oh, that's inside the loop. I'll wait 1 second, then restart the game. So here's what that looks like. I'm waiting for the game to start. Game just started. There's 10 seconds left on the clock. Here, INT 1, INT 2, timer 0. Game's over. Next game starts in RB0. So actually, player A's got a big advantage. I've got a 4-player Hungry Hippo. And that is homework set number 9. So note that you can have multiple interrupts running. Interrupts are kind of confusing, but if you can figure them out, they're really useful. Like this code would be kind of difficult to write without using interrupts. With interrupts, it's actually a fairly simple program. I've got 4 interrupts running for counters, a 5th interrupt for time. I've got the display being updated. I'm really doing 6 things at once. That's interrupts. Homework set number 9 for 376.